So chemical analysis is going to be our theme for the next 2 units. This is sort of a big intro, I guess about half the course of Chem 20. So one of the things we'll look at, not right away, is analysis by color. Certain ions have different colors, and the presence of that color can tell you something about what you have in the sample. Or if you actually study how dark the color is or quantize how dark the color is, you can get information about the concentration of that species. What we're going to be introing today is gravimetric analysis using mass of reagents, okay, and a balanced chemical equation to answer questions like when copper reacts with silver nitrate, how much silver, what mass of silver is formed. Okay, and then we can go in the lab after we predict the mass of silver. You could actually go in the lab, collect the silver, dry the silver, and weigh it and compare what the math tells you you should get to the actual silver that you got in the lab. Now, in gravimetric analysis, we need a solid product. So we need a single replacement that gives a product or a double replacement that gives a precipitate. Something like a combustion reaction that gives us CO2 gas and water vapor, there's no solid there. Okay? So we're less likely to do gravimetric analysis with combustion, or certainly would not do it in the lab. Okay? The last sort of big topic in terms of chemical analysis is with solutions. And when we do analysis with just solutions, particularly acids and bases, that's referred to as titration analysis. We're first going to recap some terms that are always true regardless of the type of chemical analysis, and then we'll specifically just talk about gravimetric for the rest of this lesson. So one key term is going to be limiting reagent. That's the chemical that totally runs out. So when we're tracking, organizing, doing our calculations, the limiting reagent is going to have a 0 concentration or 0 mass at the end. And that's going to be really important. We're going to be organizing our calculations in what's called an ICE table. Okay? The ICE table stands for how much do you have at the beginning or initially, what is the change, so how much did it go up or how much did a chemical go down, and how much do you have at the end. The limiting reagent at the end is going to have 0. And if we know it has 0, if it started at, let's say, 10 units and it ends at 0, we know the change is going to have to be down 10. Okay? The excess reagent doesn't run out. Okay? The excess reagent will have some left over at the end. We can't put a 0 in its column for the end value. That's something that we'll figure out once we've built up our skills. We'll really focus on limiting reagents, then do the math for excess reagents. So we're going to be jumping in and doing some calculations sort of right away. We're going to use our Science 10 balancing skills and use those stoichiometric coefficients that you learned how to use, combined with knowing the starting amount of a certain chemical. So we're going to look at determining the moles of water vapor produced. So how much product do we get when 25.2 moles of methane is combusted with excess oxygen? That's going to be our first example. So the tool, the strategy I'm going to use to solve this is organizing everything in a ICE table. So I, again, stands for how much do we have initially at the beginning? What is the change, C, and then how much do I have at the end? And often at the end is the answer to the problem I'm trying to solve. Okay. The change amounts always follow the stoichiometric coefficients. Okay, so every one change in methane is going to go with a doubling of the change of oxygen. So if we have 1 mole of methane, we need 2 moles of oxygen. Okay. 1 mole of methane is going to make 1 mole of carbon dioxide. And 1 mole of methane is going to make 2 moles of water. That's why we need to know how to balance. They're the predictor in chemical reactions. So these numbers, the ratio in those numbers, show up here. Okay. The I's are whatever the question gives us, and the E's are whatever happens after that change is factored in, but the C ratio matches. So determine the moles of water vapor. So there's water vapor. So this is the column we need to get to. And we want this end amount. How much is there? That will be our answer. I can write a little bit in. How much water vapor would I have initially? Well, that's a product. So that's going to be 0. You wouldn't have any product at the beginning. Hopefully that makes intuitive sense. Before you run the reaction, there's no product. Initially, 0 water vapor. Okay. Now, where can we start? We're told there's 25.2 moles of methane. Okay, that's a reactant. That would be the initial amount. Okay. Now, our stoichiometric coefficients, those are true for moles. Okay. One of these will make 2 of those, or 1 mole, because a mole is just a count. 1 mole of these will make 2 moles of those. They don't work with masses, because a certain mass of a chemical will be a totally different amount of moles for every single chemical, because every chemical has a different molar mass. So every chemical, 1 mole weighs a totally different amount. So we can't do any of these ice tables with mass. We have to use a count, and moles is the way we're going to count as chemists. So we have 25.2 moles. Okay. We're told it's combusted with excess oxygen. We don't know how much oxygen there is, but we know that's the excess reagent. So we're going to infer or deduce this must be the limiting reagent. Okay. You always have something that runs out, and then the others are extra. If we know this is the excess, this must be the limiting, and the limiting reagent always runs out, goes to 0 at the end. So the limiting reagent is going to have 0 left. So we know we start with 25.2 moles of methane. It all goes away. So the change is clearly down, is negative, and it's everything. It's all 25.2 moles. Now we're going to do the stoichiometry step. I'm going to do it orally by inspection, and then I'll do it mathematically with a ratio. Okay. We want to get the change for water vapor. What does our equation say? Every 1 mole of methane is going to make 2 moles of water. So that's a doubling, right? 1 is going to double to 2. So we should see double the amount of water vapor produced. Okay. Now, mathematically, to do this change, if we have the change of one chemical, we're going to multiply by the required coefficient. We want to get water. So I'm going to multiply by 2 and divide by the given coefficient. Given is methane, and that has a coefficient of 1. Okay. So you can either look at the numbers and just deduce what the change is. You might see a doubling to the product, or my ratio is always multiply by the required chemical, its coefficient, divided by the coefficient for the given chemical. Because sometimes the ratios might be 9/7. It's not a nice whole number. And you can just do the ratio. Okay. So our change here is going to be a double. Now this is a product being made, so the change is going to be plus. It's going up. How much? 25.2 multiplied by 2 divided by 1, and that's going to be 50.4 moles. So our water is going to have started with no moles. We're going to have made 50.4 moles. So we're going to end with 50.4 moles. So that is our answer. I don't, but I should write out a sentence saying the amount of water is 50.4 moles. Okay. And that's the end of our first example. Okay, so we're going to see the exact same thing all over again, different equation, different numbers. This one matches the copper silver nitrate that was discussed. How many moles of silver is produced when 1.23 of copper metal reacts with excess silver nitrate? You're not given the equation here. We need to write it out. I'm going to build this equation for you. One thing that confuses students a lot is how many moles of silver is produced. So that's a product, so don't write that right away. When a little over 1 mole of copper, so that's a reactant, the beginning, our reactants, reacts with silver nitrate. There's our other reactants. We have to get not hung up on that silver right away. So we have copper metal, Cu solid, metals come as one elementally, reacts with silver nitrate. Now this question doesn't really tell us the state. It only works if it's aqueous, but it doesn't say. I'm going to leave the state out, but it most likely would be aqueous. Silver is a +1, nitrate's a -1, so one of each. We do our double replacement. And our double replacement spits out elemental silver, which matches the product we're told must exist in the problem. Make sure we balance it. So we have 2 nitrates produced, so we need 2 nitrates at the beginning. That 2 doubled my silver at the beginning, so I have to double my silver at the end. So your first step is, if I didn't give you the equation, you get the equation, so you use those science 10 skills, and then we're going to start organizing everything in our ICE table. Okay. Now I'm going to be a little bit more systematic, give you a strategy. I always break this into 3 steps. Step 1 is fill out the column using some given data. So given data, copper is the only number we have. So step 1 is going to fill in that column. Step 2 is your multiply by required over given in your C line. So fill in your C's. Okay. Step 3 is the column that'll get you the answer. Silver is what we're asked about, so step 3 will be to fill in the silver. So it's almost like blessing yourself down and then across, and then you go down again. So I'm going to get started with step 1, the first column. 1.23 moles of copper. Okay. Reacts with excess silver nitrate. That's our excess reagent. We don't know how much we have. We have way more than we need. If that one is our excess, copper must run out, must be our limiting. If copper is our limiting, it's going to go to 0. Once we have 2 pieces of a column, we can fill in the last piece. All of this 1.23 moles of copper must have reacted away. So we know all of that copper reacts away, all 1.23, and we want to use that change to predict the change for our silver product. Now I'm going to fill the I in first. Products would be 0 at the beginning. How much are we going to make? I'm going to do it visually first, and then I'll do the ratio. 1 copper is going to make 2 silvers, so that's another doubling. So we should get double the product. If we do it with the required over given ratio and make it kind of more mathematical, the required is silver, and there's 2 of those. The given is copper, and there's 1 of those. So there's that 2/1 doubling. So this is being made. We have to double 1.23, so that'd be 2.46 moles. So we start with 0, we make 2.46, we finish with 2.46. So we're finally to a different reaction type than we've seen lots of single replacements. Double replacements, you've got a combustion here. Determine the moles of each product. So we've got 2 questions buried in here. In the combustion of 25 kilomoles, 25,000 moles of propane is being burned. Okay? No, propane, if you have a barbecue in your backyard and there's a big round tank, that would be propane in that tank. I'm going to get started on the equation. Propane is a gas, C3H8G. And then I know all combustion reactions have to be with oxygen. That's by definition. This is hydrocarbon combustion. The hydrocarbon reacts with oxygen and makes carbon dioxide gas when the oxygen combines with the carbon in the fuel, and it will make water vapor as long as there is hydrogen in the fuel. Okay. We need to balance this hydrocarbon combustion. So 3 carbon at the beginning, so I'm going to need 3 CO2. I always do oxygen last in combustion. Hydrogen, there's 8. And they show up in water in pairs. So we're going to need 4 waters, 4 pairs of hydrogen. And now we've got oxygen. I'm going to do a little chart. You can do this in your head. I'm going to use a visual aid, reactant, product. The oxygen's in 2 places on the product side. 3 times 2, 6. Plus, there's more. 4 times 1 in the water, 4 more. So there's 10 in total on the product side. They come in pairs, so we need 5 pairs of oxygen to get 10. And then we're doing stoichiometry. We're going to be doing ratio. So I'm going to stick that 1 in because we're probably going to need it in the required over given. I'm going to use my initial change end value ice table as an organizational tool. And now, what is the question? Determine the moles of each product. So step 1 is where we can start. We have 25,000 moles of propane. So we're going to have to start here, step 1. Okay. We're going to assume all that propane goes away and there's 0 of it at the end. Okay. Step 2 is always our change. Step 3 is getting to our answer, but there's 2 questions here for each product. So we're going to have to fill out the CO2, and we're going to have to do the water vapor. So I'm putting step 3 twice because there's 2 questions. So let's get started with our propane. There's 25,000 moles. I must well keep that prefix. We're going to assume it doesn't talk about oxygen being the excess reagent. But anytime you burn something in an open system, oxygen's always the excess. You go in the lab and you burn something, oxygen is the excess. If oxygen was the limiting, we would all drop dead because there's no oxygen and we couldn't breathe. That'd be really bad. Okay? So you can get circumstances where oxygen is limiting. You have a candle and you burn a candle and then you put a glass jar over top of that candle, then oxygen would run out and limit it. Okay? But we're assuming here that propane is our limiting. We're assuming, very logically, that all 25,000 moles of propane must be what's burning. Okay. You're going to do this in a lot of questions. It's not going to tell you the limiting excess. You're going to assume what's reacting goes away. So that's step 1. Step 2, we're going to have to do twice, one for CO2 and one for water. Let's finish CO2 and then we'll finish the water column. So there'd be no CO2 before the reaction occurs. We're going to have to do the change. So let's see, 1 propane makes 3 carbon dioxide. That's a tripling. Okay. So we don't, so 25 tripled is 75. If we do the required over a given, we're requiring CO2, which is a 3, and the given chemical is propane, and that's a 1. So 25 times 3 divided by 1 is 75. It's a product, so it's going up. So there's 75,000 moles of CO2. Almost done. We just have to do the same thing again with water vapor. But it's different stoichiometric coefficients, so it's a different mathematical answer. Visually, 1 turns into a 4, so that's a quadruple. So if we quadruple 25, that'd be 100. I can do the stoic a second time. Take the 25, multiply it by what we want is water, which is a 4, divide it by where we started, which is a 1, and that's how I got the 100. Okay. So we've seen 3 examples now using moles. We eventually have to step up our skills and start using mass to do our stoic. Okay. But this is the fundamental steps that we're going to be doing in stoic for the next 2 units. With a bit of practice, this is something you'll probably get really comfortable with after a week, and then this next 2 units can go quite well once you get really good at using and structuring things in ice tables. Okay, so gravimetric stoic, mass-based stoic. We're going to not start with moles anymore. Okay. We'll see the wording in the question change a bit. Determine the mass of CO2. Okay. This is what your tests and questions will look like. Okay. Produced when 25.4 grams, okay, so that's not moles anymore, grams of methane is burned with excess oxygen. We have to do mass to moles as a calculation, and then we know what to do with moles. We've done that 3 times. Just before I get into this question, I'm going to put up as a visual reminder how we either calculate moles or get or determine moles. So moles we can get from mass of a chemical divided by its molar mass. We're going to be using that. If we want to get mass, we have to take the molar mass of that chemical and multiply by how many moles we have. We'll be using both of these in every single question. You'll do this calculation so much, or use these to do calculations so much the next 2 units, they'll really be ingrained, and you'll be very proficient with them. Where in Science 10, you only did these for like a day, so it's not something you've really mastered yet. So our equation, I took methane. I would have to tell you on a test that that's CH4. It's not till grade 12 that you learn what methane means. Meth is always 1 carbon. Ane means that it's just filled with hydrogen. So methane reacts with oxygen to make CO2 and water. You should know that. You should be able to balance this. When I get out my ICE table, which I've pre-typed, and now you've got to hesitate. Don't stick mass into here, because 1 gram of methane does not produce 2 grams of water. 1 mole of methane will make 2 moles of water, but not mass. They have different molar masses. So we want to do the same type of sequence. We know methane, so we want to start there. Step 2 is still do our change. Step 3 is still get to our answer, which is carbon dioxide. We just have to slow down before we do step 1, and we need to get moles of methane. So it's really nice for me to label, and when you do your homework or quizzes, label your calculations. I want to get moles of methane, which is mass divided by molar mass. How heavy is 1 mole of it? What's the mass of methane? 25.4 grams. Okay. The molar mass, you grab your periodic table, you flip that open, you take the mass of 1 carbon, 25.01, and then you add to that 4 hydrogens, 1.01 each. Okay. So when you take the 12.01, 4.04 for all of the hydrogen, you get 16.05 grams per mole. Okay. Again, this is using your data table. It's not in the question. Okay. So 1 mole of methane is 16 grams, and we've got 25. We've got more. So we've got a bit more than a mole of methane. 1.58. Okay. No, I'm not writing all the digits on my board, but don't round. Leave all the numbers in your calculator, but just do a rounded version on the piece of paper. So initially, that 25 grams is 1.58 moles. But again, you kept all the digits. You haven't rounded yet. Now we know the rest of the steps. We've done them. Okay, we have our moles. Okay, all of that methane must be reacting away. We're assuming that's our limiting reagent. All 1.58 moles must react. We just had this extra step to get moles. Step 2 is our stoich. Well, this is going to be easy. 1 CO2 is made for every 1 methane. It's the exact same. Stoichiometric coefficient. They react in equal proportions. So that's a product, and it's going to be multiplied by 1, divide by 1, which I hope as an AP student you don't put in your calculator and do that. I will tease you if you do. Okay. So we must start with 0 CO2. We make 1.58 moles. So we finish with 1.58 moles, and we're almost done. I just have to turn that to mass. I'm going to have to use this equation. I need the molar mass of my product times the moles we just figured out, and we'll have that mass. So I'm going to give myself a heading. Please do this on quizzes when you do your work. Don't just do a calculation and make me figure out what you're calculating. Okay. And mass is molar mass times moles. That heading also reminds you visually of what you need to add up to get the molar mass. So what's the molar mass of CO2? You've got 12.01 in your data table for carbon. Those oxygens are each 16, so plus 16 plus 16. So the molar mass of CO2 is 44.01 grams for every mole. And there's 1.58 moles of CO2. Now I put all my units in. I know this formula is correct. It is a multiplication because my units match. Moles on the top, cancel moles on the bottom. The only unit left is grams. I carry those forward and everything is making scientific sense. Now you'd want to keep that 1.58. I don't remember how I rounded it, but you have all those digits in your calculator. You multiply by 44.01, and now at the very end you're going to round. And so my final answer is 69.6 grams. I've recorded 3 digits. This number from your data booklet has 4 significant figures, 4401. The original information only had 3 significant figures. So we're going, when we multiply and divide, we want to finish with the lower amount of significant figures, which 3 was lower than the 4 we had in the 44. So that's why I've kept 1, 2, and rounded the 3rd. I don't care where it is, the ones placed, the first decimal, the second decimal. I've kept 3 measured digits. Okay. And I should write a sentence or sum up this question. I just don't do that on worked examples. So to wrap this up, and I have it kind of set up for you, you've got the equation. An aqueous solution contains 10 grams of pure silver nitrate. Okay, so you can use that to get moles. So 10 grams of silver nitrate is mixed with a solution containing more sodium chloride than you could possibly need. Okay, you're asked to determine the mass of the precipitate. You've got 2 things to do here. First, you've got to use your solubility skills and figure out, does silver chloride precipitate or does sodium nitrate precipitate? Once you figure that out, which you can do, you need to set up your ice table and figure out the mass of which one's going to run out. So I will put the answer up after you've had time to work through this. So just getting you started, reminding you the precipitate is a solid. And please figure this out for yourself, but the silver chloride is the precipitate. Chloride with silver is slightly soluble. Sodium with nitrate is your aqueous chemical. And then where you need to get started is with silver nitrate. How many moles do you have? So AgNO3. You need to get moles, so set up that equation and solve. So mass over molar mass will get you the moles. So to finish the question, I had to deal with the mass, the moles first. So this is 10.0 grams divided by the mass of 1 silver, 1 nitrogen, and 3 oxygen. So that was 169.85 grams per mole, which is 0.0589 moles. Now I've rounded this, but I left all the numbers in my calculator. Okay, so keep all your numbers. I'm just not going to write all the digits on my board. And all of that silver would go away. I want to get to the precipitate, which is silver chloride. And this is a 1-to-1 ratio. So it's the same moles. So the hard work was getting that silver nitrate column done, 1-to-1 ratio. Okay. Once I have those moles, we've got to go back to mass. So it's a different chemical. It's why I really like to do the heading to remind yourself what to add up. Silver chloride mass is molar mass times moles. So 1 silver, 1 chloride is 143.32 grams per mole. And then we're just pulling down from our end value. 0.0589 moles. Now again, that blue number, I keep all the digits in your calculator. Multiply by that little under 144 number, and I get 8.44 grams. If you over round the blue number, you might get a slightly low answer.